In this project, the laminator software was used to optimize the properties and dimensions of a composite material to be used in an airplane spar cap. The design specified that epoxy and high modulus carbon fibers must be used. We hence selected HMS4 carbon fiber and Hexply 108 epoxy, and found the corresponding mechanical and thermal data for these materials, shown later. The design variables are the fiber volume percent in each layer, the fiber angle in each layer, and the layer stacking sequence. These were changed to optimize the weight, cost, lamina thickness, and coefficient of thermal expansion, or CTE, of the laminate. The laminate CTE is our design driver, as it should match that of the aluminum used in the airplane body in the longitudinal direction as closely as possible to prevent the airplane spar cap from breaking apart from the airplane. From the problem statement, the loads administered to the spar cap are as follows. The normal force in the x direction is 8,150 kilonewtons. The normal force in the y direction is 5,800 kilonewtons. The moment in the x direction is negative 100 kilonewtons. This diagram shows the process we use to design and optimize our laminate. There are two main iterative loops which are used. First, the loop in the bottom left corner uses lamination theory to determine if a laminate will fail. Once a laminate is found which will withstand the necessary normal forces and moments, excess layers are removed, and the layup is altered to reduce the thickness and weight of the laminate. Once these changes are made, the process begins again and the first loop is used again. This process was repeated until an optimal design was found. The table shown contains the material properties for the high modulus carbon fiber and epoxy used in our design. Data was found in Malik's textbook, Fiber Reinforced Composites, the Hexply 108 datasheet from Hexcel Corporation, and CES EduPack. All sources are listed at the end of the presentation. The smaller scope of this project meant that certain assumptions were a necessity. These have been broken into two categories: general lamination theory assumptions and other assumptions specific to this problem statement. On the left are the general lamination theory assumptions. Assumption number 1, regarding the uniform distribution of fibers in the matrix, and assumption 3, that no voids are present in the composite, enable the experimental procedure to eliminate any need to account for discontinuities in fabrication. Therefore, the distribution of stress throughout the perceived sample remains ideal. Assumption 2 allows us to assume that fracture will occur in the fibers first, and then the matrix during tensile loading, instead of through debonding. Assumption 4, that the applied force is either in the parallel or normal direction, allows us to simplify the expression of all the stresses faced by the aircraft to just these two directions, making the calculations more intuitive. With Assumption 5 and Assumption 6, we assume the lamina is initially in a stress-free state, and that all components behave in a linear elastic fashion, which means that no previous loading has caused any loss of the initially accounted for material properties. On the right, the assumptions that were made for this specific problem are stated. Assumption 1, that no loads will be applied to the component apart from the given loads, ensures that the analysis need not consider stresses and strains in the z direction. This means a thin laminate is a suitable solution for this design problem, and that lamination theory can be applied. The second assumption tells us that the epoxy matrix used exhibits viscoelastic behavior. This assumption slightly modifies the sixth assumption on the left, as epoxy does not strictly exhibit linearly elastic behavior. The third assumption comes from the data gathering process. Data for the CTE and Poisson's ratio of the Hexply 108 epoxy was not listed under known material properties. Because of this, the two values were estimated from Table 2.8 in Malik's textbook by taking the average of the same values of the nearest materials. Using the design process and assumptions shown earlier, laminator was used to find the optimal laminate. The figure shown displays the progression of the minimum laminate load scale factor, laminate thickness, mass, and cost with respect to each iteration. The first iterations focused on finding the laminate with a sufficient load scale factor, above 1. This includes a safety factor of 1.5. This led to a rapid increase in the other three design parameters over these iterations. Mass, thickness, and cost trend downward with each successive iteration, as these parameters were then optimized, while the minimum load scale factor was held above 1. The ABD matrix inverse ABD matrix, and load vector scale factors for ply failure of the final laminate are shown in these images. These were obtained using the laminator software. The final stacking sequence of the laminate abandoned the balanced and symmetric guidelines as the tensile loads from the normal load and moment in the x direction combined in the upper plies and cancelled out in the lower plies. Thus, fewer 0-degree plies were required in the lower half of the laminate. Fiber volume fraction was reduced to improve failure strain in the transverse and shear directions for each lamina. This resulted in a laminate that survives the mechanical loads while minimizing thickness, weight, and cost. The final layup is shown. The final laminate has a mass of 8.21 kilograms, thickness of 135 millimeters, or 5.31 inches, and costs $414. After the design process, does our laminate satisfy the initial problem statement? While it does withstand the necessary loads with a safety factor of 1.5 according to the max strain failure criteria, and while its thickness was reduced as much as possible, it still fails in some key areas. First, the CTE of the laminate does not come anywhere close to the CTE of aluminum, but instead comes out to a negative value. Efforts were made to close the gap, and the final laminate does this better than most, but any efforts to make the CTE positive, let alone close to aluminum, caused the entire structure to fail under the necessary loads. We therefore elected to first ensure the laminate met the required minimum load scale factor, and then worry about the CTE, and our final design reflects this. Second, our laminate has a thickness of over 5 inches, and this is after being optimized. While it will technically withstand the necessary loads, it is closer to a brick than an effective composite. A laminate this thick would not only run into complications during the manufacturing process, but would also develop stresses and strains in the z-axis, making several of our earlier assumptions very wrong. All in all, we would not consider this an effective composite material solution to the problem statement.